Hi everyone, I'm Amir Zamir. I'll be showing you some of the research that we do in the Vision and Learning Lab. Um, Keep in mind that this is a very high level presentation. I'll be showing you some of the projects very briefly, but I'll be leaving pointers on the slides, either the URL of the project page that you can visit for reading more or the paper itself. But feel free to also send an email if you had questions or if you wanted more learning material. Okay, so the research area. So one of the areas that we are very active in is computer vision. Computer vision is about understanding the visual data that various cameras in the world record for us. These cameras could be on your cell phones, or it could be on autonomous cars, or it could be on robots, and so on. And by understanding, we mean extracting various forms of abstractions from it. We can detect objects, segment objects, we can infer the 3D of the scene, we can detect the class of the scene, and so on and so forth. Another general area is perception for robotics. So these computer vision models that we develop, we are interested in ultimately turning them into a perception module for robots to enable them to uh, perceive the world intelligently and act in it intelligently, just like us humans do, and arm them essentially with that capability. And also, we are active in machine learning. Machine learning research and computer vision research these days are very overlapping, so we are very active on that topic too. I'll show you a very applied example on cross-task consistency, which is a very recent project. All right, so a little bit of why we are doing some of the things that we are doing. So generally, our research is in the area of artificial intelligence. So things are looking promising. You have probably seen this Atlas robot from Boston Dynamics that does a very impressive backflip, very good stuff in terms of control theory. There's another example. There's a cheetah robot. It's called from MIT. And this cheetah robot is reacting to the forces that come in contact with it. There's no vision in it. There's no anticipation. It's just reacting to the forces that come in contact with it. But still, it does very graceful things, very complex things. It can keep balance and so on and so forth. There's a lot of stuff in game playing. DeepMind has Atari. You've probably heard of it in DQN or Go. OpenAI has similar progress on different games. Not all the research is also recent. This is a robot from MIT in 1991. It actually plays catch very well. It can track the ball and gracefully grab it with a high accuracy. Now, all of these stuff that I showed, they have one thing in common. You notice that they are in a very controlled environment. They're either in a lab and there's a black curtain behind the robot, or there's a lab that everything is like very controlled, or they are just in an alternative world, like such as Atari. And but the real world looks like something like that. It's messy, it's busy, at times it's unpredictable, you don't even know what's coming your way, and there's a lot of things are happening. So now these robots are obviously not living in this space yet, they can't operate. We have to do many things for being able to transfer those impressive capabilities to operate in something like the messy real world. And one of those many things is vision and generally perception. And I would say actually that's one of the biggest missing pieces, if not the biggest missing piece. And that's where we are doing our research. Now, I'll show you a few of the projects, sort of baby steps towards that dreamful picture, but you can connect the dots and see how this is all belonging to a bigger picture over there. First example, Taskonomy. So like I said, vision is generally about extracting a form of abstraction from an image. For instance, like surface normals or depth or objects. These are generally viewed to be like called pattern recognition problems, and people solve them either using supervised learning. That's the most common way these days, or people are trying to solve it with unsupervised or self-supervised as well. But generally, image comes in and you extract one of these abstractions from it. But in practice, you're interested most of the time in extracting multiple things simultaneously because that's what's just useful. And also, beyond being able to extract multiple things, an intelligent system should have the capability of expanding its skills in a continual or lifelong learning manner. So this shows a tractability issue. You have to solve not only one problem, but multiple problems simultaneously, and also you have to be prepared for solving new tasks on the fly. So how we can solve this tractability issue? You might not have enough training for learning all of these. You might not have enough compute to be able to solve all of these at the test time simultaneously. You might not have enough data to transfer to new tasks or like learn new tasks from scratch if you did that. So the solution is in understanding the relationship between different problems. So solving a new problem does not become a learning from scratch. It becomes a transfer learning. And that's exactly what we did in this project in Taskonomy. So Taskonomy is a computational framework for extracting a taxonomy among tasks. And a taxonomy tells you the relationship between different entities in any space. Like in the example on the left, you can see a dictionary. The system receives a dictionary of the task that the practitioner is interested in solving, and it extracts transfer learning dependencies between elements of this dictionary. It's fully computational. It's not set by a human. And then out of those exhaustively sampled transfer learning relationships, it extracts a sparse structure. That's what you see on the right. And that sparse structure is an actionable structure among different tasks. It actually tells you that if you're interested in learning a particular problem, how it relates to the previous problem that you have learned. So you don't redo the things that you have already done. And that's where efficiency comes from. And also tells you how to transfer the novel tasks that you haven't faced yet. All right, so I didn't get into details. I don't have time, but you can visit this website, taskonomy.vision. There's multiple things there. There's an API that you can play around with it and gain some hands-on experience with the method. And the video that I showed earlier was actually the results of predictions in the Taskonomy task bank that we ran in a YouTube video frame by frame. So I can see that we're getting at a point that for one frame, we can extract multiple abstractions simultaneously from a broad dictionary. So this is actually a good step forward towards going towards a comprehensive perception module. Okay, another example is Gibson environment. Gibson is actually a simulator for active agents such as robots that want to learn perceptual skills. So in Gibson, we scan a real building and we fully reconstruct it in 3D, and we get a model like this out of it. And we use that model as the underlying data for a simulator to enable the agent in virtuality be able to learn. And that's in contrast with using synthetic data for that purpose, because if you use synthetic data, you'll have concerns about generalization to real world because the synthetic data are often very simple or they have biases. But if you use actually the underlying data, if the underlying data comes from the real world, there's less concerns about generalization because whatever complexity exists in the real world, you have recorded it at the time of recording the data set. So in the end, Gibson looks like something like this. There's a real, like a larger space, usually big buildings, whatever the scale of the building is, but the whole building is usually a scan. And there's a virtual robotic agent in it. And this robot receives a stream of RGB frames as if it had an onboard camera in that real building and some additional modalities. So here you can see that this Husky construction robot is moving around in this building and it's hitting the wall. But what's happening is that it's doing some plausible actions, and also the stream of RGB frames that it receives is something that looks plausible. It's not synthetic. And this building that you saw actually was my old building in Stanford. So we have the capability of scanning real buildings and turning them into a playground for robotic agents. And we have scanned hundreds of buildings using this method. You can go to this URL that is in the bottom of the slide. You can visit every single one of those websites, every single one of those buildings, look inside them, look at the videos, look at pictures, see how they look, and so on. And of course, you can import any agent that you're interested in learning, humanoid or minotaur or bug and so on and so forth, or a drone. And you, of course, also have to enforce physics, because if you're learning perception, you should not be able to do something that is physically implausible, for instance, sinking through the floor, passing through the wall. So we integrate a physics agent. In there, yeah, here's another example, the Mujoko humanoid. There's a popular toy robot for experimenting. It's trying to move around and it hits the door, and the physics engine correctly penalizes it by applying the force that it falls. But what you saw is that the video that you saw was plausible, meaning that if the agent was in that building and did something similar to the action they did, it would receive such a video frame. And that's exactly what we want. Now that we have such a framework, we can start training agents to solve problems perceptually for us. On the left, the Husky agent is trying to play catch with that red box. And on the right, you can see the bug that is trying to travel down a stairway using the visual signal that it receives from its onboard camera. All right, now another example that I want to show you is a mid-level vision module for robotics. So we previously saw that how we can now extract multiple simultaneous visual abstractions from a frame that comes in, and how Gibson environment gave us a possibility for supporting the learning data for that. Now we have integrated these two together, and in this paper that we call mid-level visual abstractions for navigation and visuomotor policies. So what you see in the middle is that mid-level visual abstraction that you're talking about. A frame comes in and we extract a broad set of visual abstractions out of it. And that's what goes to the rest of the framework, in this case, and reinforcement learning policy. And when the agent is trying to act, it basically acts on these more processed states of the world rather than pixels and so on. So I would refer you to the paper for seeing why that is so important, especially in terms of generalization and learning speed. But I show you just a couple examples of the behaviors that we can do with this pipeline, and we wouldn't be able to do it without that. So here is an example from a task of point navigation or point-to-point navigation. The agent is initialized in a novel building. It hasn't seen it before. It doesn't have a map. It doesn't have basically anything. It doesn't have LiDAR and so on. It only has an onboard camera, and it's tasked to go from the random initial location, which is the blue spot, to the target location, which is the red spot. So it has to plan its path completely visually, understand where the obstacles are, don't run into them, and sort of identify where the hallway would be and what's a plausible way to go from the blue spot to the red spot. You can see that this kind of planning this path is complex. So go to this website, Perceptual Actor, if you're interested in learning more about this. There's some interactive material and some more videos that you can see. All right, and we also tested this in terms of generalization to real world. So we trained agents to solve a problem in Gibson, in this case, finding this orange crate in a building and navigating to it. And we tested on real robots, in this case, a turtle bot, to go to do the same problem in the real world. In this case, it's trying to go to the twin of that orange crate. On the left, the orange crate was the digital version of it. On the right is orange crate that we printed basically orange paper and just taped on it. And you can see that actually solves the problem reasonably well. All right, lastly, example project I wanted to show you is on cross-task consistency. It's very recent from CVPR 2020 that we'll present in June. Okay, so using today's machinery for learning, for one incoming data point, if you make multiple predictions for different domains, these domains do not have to be consistent with each other. They often show contradictory information, even if they have a shared backbone. So here, this is shown over a geometric space because it's just easier to show inconsistency over geometric spaces. So for an image, a surface normal estimator says there are some bumps within that red bounding box, and depth says it's more or less flat. So obviously both of these it cannot be correct. One of them has to be wrong at least, because the underlying scene is the same. So using existing machinery, if you do multitask prediction using various forms, the outputs do not have to be consistent with each other. And as a matter of fact, most of the time are inconsistent with each other. So what we developed was a generic learning framework in which cross-task consistency is augmented in the learning objective. So the results have to come out consistent with each other. And result of that, not only, of course, the multitask predictions become more consistent, but also they become more accurate. And they generalize also better. You can see the result in the bottom row here that more fine-grained details are extracted, but also the contents are more consistent with each other. If one of the domains says there is a bump or some sort of like 3D structure over there, the rest of the domains conform to that. So now this was a geometric example. We can extend it to any sort of domain, semantics, objects, and so on and so forth. So because many domains, pretty much any domain, have some sort of conditional dependence on one another. All right. Again, I don't have time to get into details of it, but this is, again, manifestation of the issue. On top row, using existing frameworks, the amount of inconsistency is shown via the domain of surface normal. So from that incoming RGB frame, we go to a middle domain. We predict depth or shading or occlusion edges or key points and so on. And from that, we predict surface normals. We can see that you get all sort of different surface normals while the underlying scene is the same. So the fact that the upper row, the surface normals are different, is due to the reason that the underlying domains, the middle domains, introduce contradictory information. The bottom row shows the same exact pipeline with the difference that we augmented the learning with our cross-task consistency objectives. And you can see that all of them come out to be more or less the same, which means the system successfully enforced cross-task consistency in the result. So this was, again, one example. Scale it up to many domains and geometric, semantic, and so on. And for that, you would have to read the paper to see how we solve those problems. There's a lot of details involved, like perceptual losses, how to take care of ill-posedness, how to incorporate message passing, and so on. But I leave it there. Here also you can see some of the results side by side in a bigger way. Upper row is without consistency, bottom row is with consistency. You can see that the consistency in this case extracts more fine-grained details. But again, go to this website, consistency.epfl.ch, and there's quite a bit of interactive material that you can use for learning more about this. All right, so this was a very brief overview. Like I said, in the list of papers, you can see some of the papers that I mentioned and some additional ones. If you have any questions, feel free to send an email.